This lecture is on NMR spectroscopy, part 2. Remember that in part 1, NMR spectra often showed more than one kind of peak. Sometimes a set of protons showed up as multiple peaks. This is called spin-spin splitting. Why are there multiple peaks for a set of protons in the same chemical environment? In spin-spin splitting, nuclear spins of the protons interact, also called couple, with the spins of different protons within 3 countable bonds, and in a few cases 4 bonds, causing one peak to split into several peaks. OH, that is the proton on OH, usually causes no splitting and is normally just one peak. Okay, let's look at peaks that are split and peaks that are not split. In the case of a single peak, that's the situation when all the protons are not within 3 bonds of different protons, that is, protons in a different chemical environment. These are all called singlets, which is represented by S. Single peaks, no splitting. So our examples, we have X, Y, and Z have no hydrogens attached to them, or they're equal to OH, which doesn't cause splitting generally. So that would be CH3 attached to X. That set of protons on carbon would represent a singlet. The CH2 flanked by X and Y would also be a singlet, and the CH flanked by X, Y, and Z, that would also be a singlet. Now in the case of a doublet, that's our first case of splitting. You have a proton within 3 bonds of another set of protons. The proton that's causing the splitting is circled and in red. The protons that are coupled with that proton are shown in bold. So whether it's CH3, CH2, or CH, doesn't make any difference. Whether it's 3, 2, or 1 hydrogen, they're all going to turn into doublets if they're within 3 bonds of a proton in a different chemical environment. Now the reason for that is due to the spins of that one proton. They can be spin up, they can be spin down. Okay, so there's an equal chance that that proton is spin up or spin down, a 1-to-1 chance, which means that when the spins of the protons within 3 bonds interact, they have a 50-50 chance of interacting with either the spin up or spin down spin states, and thus split into 2 equal-sized peaks. We can now introduce a rule to figure out how many of these peaks we're going to get from splitting, and that's called the n+1 rule. So the number of peaks from spin-spin splitting equals the number of different protons within 3 bonds plus 1. So in this case, there's only one proton, the circled proton, within 3 bonds of the protons that we're looking at. So the effect of that one proton is to create 1 plus 1 or 2 peaks. Remember, the doublet is for the protons that are within 3 bonds of that one proton. We don't know what's happening to that one proton. Okay, we know that it's causing the other protons to turn into a doublet. Our next type of splitting is the triplet, or T. In this situation, you have 2 hydrogens that are within 3 bonds of a different set of protons. Those are the ones circled in red, the ones that are going to cause the splitting. The reason that you get a triplet is due to the different combinations of spin states for those 2 protons. You can have 2 spin down, or 1 spin up and 1 spin down, but there's 2 possible permutations of that. And finally, you can have 2 spin up. So given the number of possible orientations of spins, we have 1 for the 2 spin down, 2 for the 2 permutations of spin up and spin down, and 1 for the 1 permutation of 2 spin up. So that gives us a 1-to-2-to-1 ratio of different spin states, and thus because that's what's perturbing the spins of the other protons, we get a 1-to-2-to-1 ratio of peaks, a triplet. Again, we follow the n+1 rule. So there are 2 protons within 3 bonds of these different protons, and that gives us 2 plus 1 or 3 peaks. Now with the quartet Q, we have 3 circled protons within 3 bonds of a different set of protons. Now in this situation, that could only be CH3 next to a CH2 or CH3 next to a CH. CH3 next to another CH3 is just ethane gas, and that would not cause any splitting. They'd be equivalent protons. So why do we get 4 peaks, a quartet? Well, how many different ways can you combine spins of 3 protons? Well, the following ways. You can have 3 spin down. You can have the permutations of 2 spin down and 1 spin up. So you can have 2 spin down, 1 up, or you can move that spin up in the middle or in the first position. So you can have spin down, spin up, spin down, spin up, spin down, spin down. There are 3 permutations there, 3 chances for that type of spin. And you can also have 2 spin up and 1 spin down. There are 3 permutations for that. And finally, 3 spin up. So there's a 1 to 3 to 3 to 1 ratio of these different spin states for the methyl group, and thus that splits the protons within 3 bonds into 4 peaks with a 1 to 3 to 3 to 1 ratio of peaks. Again, applying the n+1 rule, you would have predicted there would be 4 peaks because there are 3 neighboring protons, and 3 plus 1 equals 4 peaks. Lastly, we come to the multiplet. As you can see, it's a whole bunch of little tiny lines very close together. And that's because there's a lot of splitting going on. With the multiplet, or M, we have a CH2 or a CH flanked by a whole bunch of different protons, not just one set of protons, but 2 or more sets of protons. We could designate these protons as H sub n and H sub m, or in the case of CH, where there are 3 different sets of protons around it, H sub n, H sub m, and H sub y. Now in the case of the multiplet, the n+1 rule does not apply unless the neighboring hydrogens are all identical by symmetry. If that's the case, then you can just add them all up and add +1. For different sets of neighboring protons, the number of peaks is equal to a much more complicated equation. It's the number of protons of type n plus 1 times the number of protons of type m plus 1 times the number of protons of type y plus 1. So for example, if all of the different protons surrounding CH are different, then even if n, m, and y are all the same, they're all equal to 2, the number of peaks would be 2 plus 1 times 2 plus 1 times 2 plus 1, or 27 peaks. And again, you couldn't count those peaks. They would be too close together. They would be all mushed together. If, however, all of those protons, all of those CH2 groups were identical by symmetry, then we'd simply add them all up. We'd get 6. Add 1, we'd have 7 peaks. In the example shown, okay, there's our symmetry situation because the CH2s are all attached to X. So the proton that's being flanked by all 3 is going to have 7 peaks due to symmetry. And in the case on the right, all of the different groups attached to the CH2s are different, so therefore we get the maximum splitting of 27 peaks. Again, you do not count how many peaks there are. You just know that a multiplet is a mess. It's surrounded by, a proton is surrounded by lots of other protons, different sets of protons, so that's why you're getting such a large number of peaks. Okay, we're going to take a look at the proton NMR spectrum of methyl propanoate again. This time looking at the splitting that's present and figuring out why it is what it is. So if you look at protons HA, those protons in the methyl group are not within 3 bonds of any other protons, therefore it's a singlet. for the protons in CH2, Hb, that's within 3 bonds of a CH3. So therefore, by the n+1 rule, we should turn into 3 plus 1 or 4 peaks, which is a quartet. And Hc is a CH3 group next to a CH2 group. So the CH2 group causes you to have 2 plus 1 peaks for Hc. That would be a triplet. Here's a second example showing how we arrive at certain kinds of splitting. For this ester, the HA protons are CH3 that again do not have the protons within 3 bonds of any other protons, so the HA protons are a singlet. The HB protons in CH2 are within 3 bonds of another CH2, therefore you get the 2 plus 1 rule applies, so the HB proton should represent a triplet. The HC protons are flanked both by CH2 protons and CH3 protons. That automatically means that the HC protons are going to be a multiplet, getting as many as 2 plus 1 times 3 plus 1 peaks. Again, we don't count them, we just see that mess of peaks for HC. And the HD protons, the CH3 group, are adjacent to 2 protons in CH2. So that CH3 group for HD will become 2 plus 1 peaks, a triplet. Here are some 4-bond coupling cases. If you have protons on a benzene ring that are within 4 bonds of each other, and they're in different chemical environments, we can call this W coupling because if you inscribe the bonds, it looks kind of like a stretched out W. That will give you some coupling that will be detected in the proton NMR spectrum. The typical kind of coupling that you see in a benzene ring is known as vicinal coupling. That's when the protons are within 3 bonds of each other, and the spacing between the peaks in that kind of a doublet is between 7 and 10 hertz. Whereas with the W coupling, the 4-bond coupling, the spacing between the peaks in the doublet is much smaller, only 2 to 3 hertz. So sometimes it's hard to see in a proton NMR spectrum. Our second case is that of an alkyne, a terminal alkyne, in which the proton attached to C triple bond C is within 4 bonds of another CH. In the case shown, it's within 4 bonds of a CH2. So that proton on C triple bond C, the terminal proton, is able to cause CH2 to become a doublet. Correspondingly, the CH2 group with 2 protons following the n+1 rule, 2 plus 1 equals 3, causes the terminal proton to become a triplet. In the case of the allylic protons, that is CH adjacent to C double bond C, we can get coupling between that CH proton and a proton attached to the carbon-carbon double bond, another type of 4-bond coupling. So we see that the CH2 group becomes a doublet, again a very narrow doublet, which you may or may not be able to see, because of being within 4 bonds of that single proton on the double bond, and then correspondingly there's a narrow triplet caused by the CH2 protons splitting that CH proton in the double bond. Here's an example of 4-bond coupling. We have a terminal alkyne in which HA is within 4 bonds of HB. HA becomes a triplet because of the 2 protons in CH2. 2 plus 1 equals 3 protons using the n+1 rule. It's a very narrow triplet. Normally, in order to tell that that's a triplet, you'd have to blow up the spectrum, expand that region of the spectrum to tell that there are really 3 peaks in a 1 to 2 to 1 ratio. HB is coupled to HA and therefore becomes a doublet, 1 plus 1 equals 2. And again, it's a narrow doublet, but much more obviously a doublet as compared to the triplet. These are the 4-bond coupling interactions. Again, you see that the visible evidence for splitting is a little bit more difficult than in the 3-bond cases. Practice problem 3. On the following molecule, draw and label the sets of protons in the same chemical environment, HA, HB, etc., and determine the splitting, D for doublet, T for triplet, Q for quartet, M for multiplet, or a lack of splitting, S for singlet, on each set of protons. Ignore 4-bond coupling in this problem. At this point, you want to pause the video in order for you to work on the practice problem. Answers to practice problem 3. For the HA protons, those protons are not within 3 bonds of any other protons, and therefore the HA protons all represent a singlet. The HB protons have symmetry, so those protons will show up in one spot, in this case represent a doublet, because those HB protons are within 3 bonds of the HC protons. Correspondingly, the HC protons are within 3 bonds of HB protons, and again you get a doublet due to the n+1 rule, 1 + 1 = 2. Now we could say that there is splitting between the HC protons and the HD protons, but as we were instructed, we should ignore 4-bond coupling because it's very tiny in this situation. So we only give a doublet for HC protons. The HD protons are within 3 bonds of the HE protons. There are 3 HE protons, so 3 + 1 = 4, so the HD protons become a quartet. The HE protons are, of course, within 3 bonds of the HD protons, and there are 2 of those. So 2 + 1 = 3. That gives a triplet for the HE protons. Practice problem 4. On the following molecules, draw and label the sets of protons in the same chemical environment, HA, HB, etc., and determine the splitting, D for doublet, T for triplet, Q for quartet, M for multiplet, or a lack of splitting, S for singlet, on each set of protons. In this case, include 4-bond coupling. At this point, you want to pause the video in order for you to work on the practice problem. Answers to practice problem 4. In part A, we have 3 sets of protons. The HA proton is a CH3 group. It's a singlet because it's not able to have splitting within 3 bonds, and it doesn't have any of the special 4-bond coupling. HB protons are in the CH2 group. They're within 4 bonds of the terminal proton of the alkyne HC, and therefore they become a doublet. And HC is, of course, within 4 bonds of the HB protons and becomes a triplet. In part B, we have 4 kinds of protons. The HA protons are on the methyl group. They are not within 4 bonds of any other protons, and therefore they are definitely a singlet. The HB proton is within 3 bonds of the HC proton, and that's it, so it becomes a doublet. The HC proton is within 3 bonds of HB, as well as within 4 bonds of HD. The interaction between the HC spin and that of HD is W coupling. So we have 2 different types of splitting. HC split by HB creates a wider space doublet, and then we split each of those peaks again by HD's interaction to get 2 sets of doublets. So one can call this a DD, a doublet of doublets, or simply M, a multiplet. HD is only within 4 bonds of one other proton, that's HC, through W coupling, and so it produces a narrow spaced doublet. Now we'll look at the steps for solving molecular structure from proton NMR and IR spectra. Given the molecular formula, you can often figure out the exact molecular structure of an unknown from its proton NMR and IR spectra. And here are the steps. First, calculate the degrees of unsaturation, the DOU. If the DOU is greater than or equal to 4, check the proton NMR spectrum for peaks, or a peak, in the 6 to 8.5 part per million range. That means there's a benzene ring. If there are peaks in that range, draw benzene. Benzene has a six-sided ring and 3 pi bonds. That makes 4 degrees of unsaturation. Look for all pi bonds other than benzene in the IR spectrum and draw them as separate pieces. Look for a terminal alkyne, H attached to C triple bond C, OH, NH, or NH2 in the IR spectrum, and draw those as separate pieces. From the proton NMR spectrum, use integration and the number of hydrogens from the formula to calculate the number of unique hydrogens for each set of peaks. Assuming no overlap with other peaks, throwing off integration, you can know that one hydrogen equals CH, OH, or NH, 2 hydrogens equals CH2 or NH2, and 3 hydrogens equals CH3. Draw these as separate pieces. Note that if your formula doesn't contain oxygen or nitrogen, then of course OH or NH is not possible. From the proton NMR spectrum, use spin-spin splitting to figure out neighboring sets of protons, allowing you to finally connect pieces. You never connect the pieces unless you have splitting information to confirm they're connected to each other, that they're neighbors. Ignore multiplets. They'll come out right in the end. For example, a triplet for CH2 and a quartet for CH3 means that CH2 is connected or attached to CH3 and no other neighboring hydrogens. If more than one structure is possible based on splitting, use chemical shift values to decide which structure is correct. Only do this if you have to. Surprisingly, the chemical shift information is not used as much as you might imagine. You really use the integration and the splitting more than anything else, and the chemical shift information is only necessary when you really have to figure out whether or not you have one structure or alternative structures. Practice problem 5. Determine the structure of the compound whose molecular formula and IR and proton NMR spectra are shown. Justify your answer. By justify your answer, I mean explain how you know what you know. How do you know that you have a CH3 or a CH2 or a CH? How do you know that they're next to each other, that the CH3 is next to the CH2? I mean, that's what you need to prove. You need to use integration and you need to use splitting. And if you have more than one possible answer, you need to use chemical shift to determine which answer is right. The IR spectrum for this problem is on the next slide. At this point, you want to pause the video and go back and forth between the two slides in order to work on practice problem 5. Answer to practice problem 5. Well, first we calculate the DOU, which is 10 plus 1 minus a half of 13 minus 1. So we have 11 minus 6 or 5 pi bonds and or rings. That's a DOU greater than or equal to 4, so we automatically look for benzene peaks in the proton NMR spectrum. And there they are, we found it. So there's a benzene ring present in this structure. We draw that down immediately. Continuing with our answer to practice problem 5, now we look at the infrared spectrum and we find that there is a C double bond O between 16 and 1700 wave numbers, which would correspond to the C double bond O in an amide. And you might think, couldn't that be C double bond C? Isn't that in the right range? That's possible. We're going to stick with the amide for now, and we're going to see whether or not C double bond C is really relevant in the structure. We've now figured out all the degrees of unsaturation, 4 for benzene and 1 for the C double bond O. Answer to practice problem 5 continued. Now we look at the integration from the proton NMR spectrum. To get the number of hydrogens, we add up all the integral values, multiply them times x, and set them equal to the number of hydrogens. So we have 1 plus 0.4 plus 0.6 plus 0.6 all times x equals 13. We get 2.6x equals 13, and thus x equals 5. So that's the factor by which we multiply each of those integrals to get the actual number of protons in those regions of the spectrum. So we get integration values converting to 5 hydrogens, 2 hydrogens, 3 hydrogens, and 3 hydrogens. What does that mean? Well, we know that the 5 hydrogen area is where the benzene ring is. So those are 5 hydrogens on benzene. That's a phenyl group. The 2 would represent the CH2 group. There are no, well, there's a possibility of the NH2 group, but we didn't find NH2 in the infrared spectrum, so it has to be CH2. Then the 3s are, of course, 2 CH3 groups, which are in different chemical environments. Note that if you add up all the carbons, we're only left with one other carbon. So therefore, our initial idea that the infrared spectrum was showing a C double bond O and an amide is correct. It can't be C double bond C because that would be too many carbons. Here's the last part of the answer to practice problem 5. We have all the pieces, we just have to figure out how to put them together. That's where splitting comes in, right? Remember, that tells you who is the neighbor to another piece. So if you look at the quartet for CH2, that means that there have to be 3 hydrogens within 3 bonds of that CH2 to turn it into a quartet. That would mean that the CH3 is attached to the CH2. So when we put those together, we get an ethyl group. The CH3 is a triplet because it's within 3 bonds of the CH2. And that all works. Now we have the benzene ring, which looks kind of funny in our NMR spectrum. It's got a lot of jagged peaks. But that makes sense because you have protons in different chemical environments within the benzene ring, and there's splitting by more than one portion of the ring. So you're going to get a multiplet type of pattern. And then we have our singlet due to the other methyl group. So when we try to put all these pieces together, including the amide group, we get 2 possible answers. Structure A has the ethyl group attached to C double bond O, and structure B has the ethyl group attached directly to the nitrogen. But which structure is correct? Now you have to use chemical shift information to distinguish between structures A and B. B has to be the correct structure because CH3, the singlet, has to be near a 2.0 part per million chemical shift region. That works in B. However, in A, CH3 would be between 2.9 and 3.9 parts per million, which is too high. So our correct answer is B.